So I'm going to try to cover the machine building assignment in a way that causes as less confusion as possible. And it's not going to be like one tutorial where let's say show you the CAD design basics for machine building and how to integrate it with the other parts. So there, if I would need to cover all of the machine building, then these would be probably at least 3 different tutorials. I would say like 5. So I will just try to give you a good overview of what we have and what is the shortest path possible for us to succeed. So here we have the overview. So the goal of this week is to create a machine that has a mechanism, actuation, and automation element. And I already talked about this earlier, but the approach is going to be to split into teams and do documentation. Each team then also individually, each team individually, and then also we'll have an overview page. And then, I will show what parts do we have and give you hints about where to find them. So yeah, the goal, so mechanism is so we should make use of the available parts and the digital design and fabrication methods that we already have acquired in order to build a mechanism that you can operate manually. So that's for the mechanism part. So you should be able to put things together in a way that you can move them with your hands. So if it's a grinder, you should be able to turn the milling part and operate it manually. If it's a 1-axis or 2-axis machine, you should be able to move the axis around. Then the actuation part is where electronics and motors come in. So we should make use of the available motors. So we have a lot of different stepper motors here and also driver boards. So those we have also different flavors. So you should use a combination of those, and you should be able to control the motor by using electronic signals or pulse width modulation and things like those. So yeah, and so you should be able to build a solution where you have a controller board which is controlling the motor, and then the motor would be connected to the mechanical part of it. So that's the kind of the part where these two things connect. So you should be able to connect the actuation part to the mechanism so that the mechanism is driven by the motor. And then the automation part is so the control interface for the machine that you're going to build. So your machine is going to have a specific functionality, and that specific functionality, it requires a specific kind of automation, so a specific kind of interface. Let's say if you have a drink mixing machine, then you should be able to select the components that you want to use for your drink and define proportions, and then let's say hit the button mix, and then the machine would do the rest. If you have let's say a lathe, then you should be able to define the speed of the lathe, the position of the cutter, so like a CNC lathe, and you should be able to define how that cutter is following a certain path. If you have, let's say, a 3D scanning, a photogrammetry device, then you should be able to send like a specific angle, how the bed is turning, and then be able to snap a picture digitally, like from the computer. So you should have some sort of an interface on the computer that lets you control the actuation part. So which means yeah, so that you have a computer program. So in a similar way as the SRM20 machine, let's say that has, so that there's the machine. So on the computer, you use the V panel in order to control the machine. And then in between, in the machine, there's also a controller that actually drives so the machine itself. It's two parts. It's the motor controller, like a board, and then the mechanical part itself. And then the approach, yeah, I told, so we're gonna have a team of 3 people each. One person is gonna do the mechanism, one is gonna do the actuation, and the other one is gonna deal with the automation. And then as for the documentation, so we're gonna make repository, a separate Git repository for the machine files, so that how I would like you to approach this is that you basically, let's say you're building an open source machine project. So you would you'd use the Git repository where you would put the source files, and you would also put instructions how to assemble them together, and how to install the software and so on. So where to find it and so on. And then on your individual pages, you should describe the process more as a story that I did this experiment, I found out that, and based on that, I made the design, and I printed this 3D printed part where I can insert the bearing, and that failed, and then I did it again. So yeah, so individual part is important. Then the group part is, which is more like should look like an official machine building, so open source machine project. And then I'm gonna have this, so for the official Fab Academy students, I will have the lab page where I will have a picture and short description of the machine and link to the repository, where then there's gonna be the more information about what the machine does and so on. And then for Alto students, so we're gonna do it in a similar fashion. I'm gonna have the groups listed on our digital fabrication page, and then the links to the repositories there. And then as for the complexity, so you should be able to send messages from computer to the board to drive the machine. And you should generally aim for a minimum viable product that works. It's not necessary for it to be perfect, because we have just 1.5 weeks, and we should just use this time so that all of you can understand, how to put these things together. So how generally a machine works, and then that should work as a framework for further development in terms of your final projects and whatever machine you want to build in the future. And then as for the parts, we have some mechanical parts. So there's a variety of parts that we have gathered from old 3D printers and other machines here at the lab. So most of the parts you can find at the white, like at the one of the bigger tables on the lab. So when you enter the main room, so it includes bearings, rods, motors, gears, and also electronics. So I put some motors over there and controller boards. So yeah, electronic parts. We have stepper motors, 2 driver boards, many step sticks that can be used for the Fab Arduino stepper shield or other solutions. And then for automation, yeah, you will need a board, like a bigger board. So yeah, this Arduino shield is recommended because it's fairly easy to make. And then we have also one TinyG controller board. So those can be used. So there's some pictures of what I mean. So there are rods with linear bearings over here. Then we have these lead screws and just the plain rods. Then we have these aluminium profiles that can be used in order to make the basis of an axis or several axes. Then we have a bunch of all kinds of mechanical parts that can be used in order to put something together. So these wheels can be used in order to drive onto sort of a rail. So you can make a rail out of an aluminium profile, or you can 3D print it, or CNC mill it, or laser cut it. Then let's say this qualifies for mechanical part with actuation implementation. So you see there are two motors. So one motor is controlling the axis, and then the other motor is controlling the rotation of this. I think it was supposed to be a camera slider. And you see that there's some parts that are reused. So the rods are being reused, and then there are custom-made parts which are holding those more precise, more rigid parts together in a specific way that is specific to your machine. And there's another example from the students last year. So this was supposed to be, like camera turning machine. So there's also sort of a camera slider, but you would put the camera on top of it, and then it would be able to turn it around. And it would feature this Arduino shield. So this is like a mechanical part with already like a actuation integration. And then when they did the interface, so the interface that would then send messages to this Arduino board, which would then forward the necessary currents to the motors, so that they turn the so this belt, and I think this is 1 to 4 translation in terms of mechanical translation. Should and the way how this is built is also, you see there are 4 bearings which are holding this disc. So this provides the stability of rotation. So if you want to rotate something that is bigger, then using one central rod for turning, it's most likely to make this disc unstable. So it's going to wobble a lot. In order to prevent that, so you can use a system like this. So there are 4 bearings or more bearings which are actually holding the disc. So the weight distribution is much more even. And then you can use different ways. You can anyways use a central rod to sort of turn it around, but probably like with a belt drive like this, it's gonna make it easier for the motor to turn it. So the motor does have like a certain torque limit. So if you make it like this, then you need less force for the motor in order to be able to turn this. And thus you can support heavier objects here, for example. And also don't forget that you will need a power supply. So for a bigger motor, the bigger the motor, the more power you will need. And we have a few of those, so which are specifically for machine design. And then we also have some that we have salvaged from older computers. And yeah, these are the stepper motors that we have. And that's the TinyG board on the left side of it. So we have shields, or the other one is board. So the one on the top left is the Arduino fabbable stepper shield. So it has a project page. I would like you to actually focus on this one. It's going to be fun making it. So we have all the parts and also the step sticks and Arduinos. And then we have one of these. Both of them are open source. So let's check the shield first, actually. So here we go. Yeah, so this is the stepper shield documentation page. You can find it also from the Fab Academy project listing. But yeah, for now, just check this page. But I think if you enter stepper shield in Google, then you would be able to find this. And so one of the things that I mentioned is that you might also accept the challenge that if you're building one single axis machine, then you could explore this design and try to quickly design a board which supports only one of these step sticks. And they have an interesting shield milling app, so which is also being able to generate toolpaths for the SRM and MDX40 machines. And here you have the opportunity also to learn how to use rivets. So this is not necessarily, this is not a double-sided board, but in order to be able to install these headers, it's designed in a way that you need to drill these bigger holes in order to insert the rivets, the 1.5 millimeter rivets in outer diameter. Yeah, and we have also all these parts listed here at the lab. And then the other one is the TinyG. And all the information that is related to TinyG you can find here on this page. And it has 4 motor drivers on the board already. So which is sort of, it's less flexible than this one, for example, because so these step sticks, so you can, whenever, as soon as, whenever a new stepper driver comes out, so somebody might create a step stick, or you yourself, and you could just plug in a better stepper driver in the existing solution instead of ordering a new board where you need to resolder, or resolder these chips, so to say, risking to damage your board. But yeah, so this is kind of also more or less a standard. So many 3D printers are using this as the main driver. And here you can find all information about how to use it and what is it about. So it's basically an Arduino with stepper drivers. So basically same thing as using an Arduino with this shield. And yeah, the step sticks. So here, so from last year, so I ordered a bunch of Trinamic TMC 2208 silent step sticks. Then we have some older MakerBot and different step sticks from older machines that we salvaged from the other 3D printers. And here you can find the documentation about those. So data sheet and so what they are supporting. So we have this TMC 228s, 2208s. So you can supply, you can use motors up to 36 volts to the support current, voltage up to 36 volts. Phase current, so yeah, probably maximum 1.2 amperes. Then you can go up to 256 microsteps. So it's probably like fractions of a step, which is quite impressive. You change the step direction, have a serial control over it.
Sorry, what's the step stick used for?
So it's just a unified standard for breaking out a stepper driver chip. So these chips, they are different in size and shape, but then the actual functionality of those is quite similar. So usually you just need to give it a pulse in order to drive a motor one step forward. But then, so these are, if you make it in the form of a step stick, these are easily replaceable. So you could, let's say, try out 5 different step sticks and find the one that fits best for your design. So in terms of quality, price, so there are different things that you might need at a certain given point. So let's say you want to make a cheaper machine and you don't care about if it's silent or if it's precise, then you can go with a cheaper step stick and stepper board and stepper driver. And then if you need higher quality, then you might go with in some scenario with a better stepper driver, which is So it's just the replaceability of it. So this makes it much easier to experiment and replace the specific motor driver.
So it's driver.
Yeah, it's basically a motor driver, but with a specific format.
Okay.
So it usually has this layout.
And it's also like when you're driving stepper motors, usually like you don't like with a normal motor like a DC motor or something, you would rather like just feed it some voltage and then have it running at that voltage, like whatever, and then control the voltage. But when you're working with stepper motors, you want to kind of precisely control the current that goes every single pulse when you move that, like a stepper motor moves by
Right.
discrete steps. So you want to control accurately the current that goes there. And these stepper motor drivers, they don't really care about like they do care about to some level of like what voltage you feed into them, but it's more like you can precisely control how much current is going to be sent to the motors. So they have like a variable setting. There's a little potentiometer there that Chris is showing that you can set how much current goes there, and it's just like just a very handy way of controlling stepper motors and a precise way, and also like a way that keeps the power in control, so that you don't have to worry about overheating or like you have to worry about overheating, but it takes care of a lot of the things for you when you work with these drivers.
Okay. Yeah.
So for the output week, you'll be encouraged to actually make one driver yourself. So make a board which includes either a ready stepper driver on it, or it uses H bridges or like plain MOSFETs. And this simplifies it a lot. So it makes it less error prone, so to say. So, and for this week, it's perfect because like it's just basically you have to learn, you have to do a little bit of customization or design yourself, and you should be able to put together a unique solution by using existing modules. And yeah, so this is the board that we have here. So that's also one of the Trinamic 2208 step sticks. Should watch which direction is on which side is on top. And then for the automation part, so these boards, they use GRBL. So as for the stepper shield, Arduino is as the base, and then you install GRBL interpreter on it basically, which makes it it to appear as a serial device on the computer. And then you can use this serial connection to send GRBL messages to the Arduino, which are then being translated into the motion of the motors. And you can find more information about GRBL over here. So yeah, you can find information about all the features that you might need here in terms of making this work with your board. And then what I want you to do in terms of automation, to explore possibilities, how you can build your own interfaces for the machine. So this one, so here you can find already like Python examples that let you send GRBL messages to the Arduino via Python. So here you see that you need to define the serial line with a specific baud rate. And then you're going to use this connection in order to send GRBL G code to it. So here it's reading a file and then sending some new lines to the board, sleeping for 2 seconds, then flushing the input. And then for each line, it is basically sending this to the serial line. And each line is being then interpreted as a GRBL command. And let's say it sends the motor to a certain position. And it's also collecting what the GRBL board is reporting back. So yeah, you can use so these test scripts as the entry point for building a local server for your interface. And then, yeah, I propose to use a web interface solution. So since you already mastered some HTML, CSS, and JavaScript in the web design week, so you can use any of the available UI frameworks if you're into it. So Bootstrap is fine. If you want to dig deeper into web development and app development, web app development, then you might use Vue.js and other things. And what you should do with the web interface is to be able to connect to this Python server and send messages to it, so it forwards then these messages to the machine. So, and basically you should have this simple interface on the computer, so which is really directly related to the minimal functionality of your machine. So let's say you want to turn one step forward and then you want to snap a picture. So these are two buttons. You click the turn, so the message is being transferred to the board, and then the board controls the border. And yeah, that's what you should achieve during the next 1.5 weeks. So yeah, one more time about the documentation, that you should individually document what you did, and especially interesting is how you failed and how you recovered from that fail. And then as for the group, you'll have a machine repository. Think of it as an open source machine documentation page. And then as for the class, I will add the final results, images, and short description on the relevant pages. So for the official students, it's going to be in the Fab Academy repository and the Fab Academy lab page. And for us, it's going to be the class page, which we've been using to manage the websites of ours. So that's it.